recording. So what is important in data pre-processing is, first of all, we should get what is there in the data, then what problems we have, or do we need to transform the data into some other form so that we can apply more algorithms to that. So that is the thing which we need to discuss today. So these are the topics which we are going to discuss in data pre-processing: aggregation, sampling, discretization and binarization, attribute transformation, dimensionality reduction, feature subset selection, feature creation. Aggregation means, can we combine two attributes into one attribute? That also will help reducing the features. That also may bring more value when you consider both features together. Then you may see more value. It's understanding what that feature and how it describes the data. Combining two or more attributes or objects into a single attribute. What is the purpose of this? Obvious thing is the data reduction. Instead of having two features, you have only one feature, means you reduce the data representation at least. Reduce the number of attributes or objects. Change of scale. So when you have something, let's say every hour you want to measure something, let's say how much of production is happened, then the scale means the number of units produced will be very small number. Instead of taking into every hour, if you consider, let's say, all hours, 24 hours put together and what is the output in a day, then you'll get a bigger numbers. So change of scale. In other words, let's say here, another example is given. Cities aggregated into regions, states, countries, etc. If you go by city type statistics, city-wise statistics, you'll get less numbers, small numbers. But if you combine all cities together and if you represent the whole thing as a region, like Telangana state instead of Hyderabad, Vijayawada, like that, or Hyderabad, Warangal, which cities are there in Telangana, instead of representing each city as a separate thing, you can just put aggregate them into one state. Then region, states, countries, etc. We'll see some examples for these. Days aggregated into weeks, months, or years. So instead of having each day, then you aggregate them into weeks. So if you have 365 days data, then 365 columns will come. Instead of that, you'll write how many weeks? 52 weeks. So week-wise data you will represent in the data. Then you reduce your 365 day-wise columns to 52 week-wise columns. Then you aggregate the values. In that whole week, whatever is there, those values to be summed up. Then more stable data also. Another advantage for aggregation is more stable. So there may be variations, let's say one day less, one day more. But when you bring together week-wise, then mostly week production may be same. For all the week, when you compare day-wise productions, there will be lots of differences in each day compared with weeks. Because in week, you have chance that some days less, some days more, then automatically it neutralizes that less and more. Then you see stable data. Means stable production. If it is a production, then stable production in each week. Maybe X units means next week also X minus 1 or plus 1. But if you take day-wise, then someday it may be off production may go down, off production may increase, all those things, let's say, depending on that day, weather, other conditions, those things. So more stable data. Aggregated data tends to have less variability. Stable means less change, less differences we'll see. So one example is given, precipitation in Australia, then variation of precipitation in Australia, standard deviation of average monthly precipitation. If you take a monthly precipitation, then the spread is more, means more distinct values you see monthly wise. The right side thing is giving less precipitation, means there are less variance. Variance means less number of distinct values you see here. The right side for average yearly precipitation. They aggregated monthly to yearly, then they plotted it. In yearly, you see it. See the spread is less, means different values, which is it is taking. Whereas monthly wise, it is taking more. So the variation right side is less, left side is more. So that is what the advantage when you aggregate, it becomes more stable. So if you want to see the stable, then the data science is not only for predictions, classifications. So if they want to see that, what is the stable production, you tell me, the time, which time it is, you see the data is stable. Then these type of things are important when we want to present. This is called descriptive analytics. So day wise, there is more variance, but when we see that production weekly wise, there is not much variance. They're almost same in each week. That is also important for some of the people, when they want to supply, then day to day, they may not give guarantee, but they may say that every week we will supply this much, because week wise the production is stable. So supply also they can make stable. That is aggregation. Yes.
Sir, in the previous plot on x-axis, did they represent the standard deviation?
Yes. How much, how many days with the 0 value, how many days with 2 value, how many days with 4 value, like that. Okay. Then there are precipitation 4, after 2, the precipitation is very, very small number. The number of years with precipitation 4, very small, right? You don't have many. But when you see in monthly precipitation with the value 10, there are many. Precipitation with value 5, there are many.
Yes, sir.
You see the spread. Spread means the day to day wise, if you monthly wise, if you compare, then the lots of differences between precipitation of months. When it comes to the yearly, maximum is with 140, 160 is happening between 0 and 0.5. You see the maximum data, you see the area.
Yes.
Within the small values, you are getting that.
Yes.
So the stableness is coming here in yearly wise. Even the highest is also 140 a year. Whereas in monthly wise, the highest is how much? 180. Lowest is 0. The variance is also less now. The way it is varying only between 0 and 140 in yearly. When it comes to the monthly, it becomes 0 to 180, means you see more variance also. Then the next is, if we cannot handle the entire data, sometimes it may take more time, it may take, you may not have enough tools to handle the entire data, then can we get some idea by taking sample of the data? Can we describe what is there in the data or what we can find in the data? So one method, such method is called sampling. Take a sample and find out properties from the sample, then see how much you can describe the entire population. The key principle for effective sampling is the following. Using a sample will work almost as well as using the entire data set if the sample is representative. What is the meaning of representative? A sample is representative if it has approximately the same properties as the original set of data. We discussed earlier also this sampling. So representative means if there are 50% of the, if you take a population and their income, and if both, let's say in the population you have a 52% male, 48% female, when you take a sample, it is representative only if again the sample consists equal proportions, 50 2% male and 48% female. Similarly, educated people. The sample will be representative when you are computing the income or gathering the income of the people. Then you should have same education standard percentages, what it is there in the population. In the sample also, it should reflect same. You cannot just take the only highly graduated people and their income, then that won't represent average income of the population. So representative means it should represent perfectly to the population. So whatever percentages of different sex you find in the population, it is expected in the sample also, in the same percentages you should have that. Then it is called representative. Is it clear what is representative? A sample of the population?
Yes.
Sample size. So what will happen? It's a representative sample is given here. 8,000 points, 2,000 points, some image is taken. Out of image, you are selecting 8,000 points. And 2,000 points you are selecting. 5,000 points you are selecting. You see it is representative, all these things. Even though sample size is small, is it representing the same image or not?
Yes.
So if you take sample only the first part, it won't represent, right? They are spread over those points. Even it is 500 points, but they are spread over from the entire image. You are not taking only from particular part of the image. If you take particular part of the image, these 500 points, it won't be represented. You still get idea. What is this? Let's see. What is this? Can anybody say? I cannot figure it out, but some JS, something like that.
JIS.
Yeah, JIS. So still you can, but when you take the small sample, it is difficult. When you take medium size, with a little bit effort, you can find. If you take a more big sample, it becomes easy, right? Then as sample size increases, then it exactly represents, or you can actually attribute whatever you find from that sample to the population. Means sample size is bigger means what? You are taking entire population. So then we should have some balance so that it's a, if you take the entire population, then there is no need to call sample. So there should be some balance that it's a, with some, you should be able to get a representative sample as well as not very high number of sample size, very big sample size, which is almost equal to the population, then our purpose will not solve. So both need to take care. Sample size should be small and it also should be representative. Then types of sampling. So how do we do sampling? There are different types. Simple random sampling. There is an equal probability of selecting any particular item. Randomly, we will pick up elements from the population. Sampling without replacement. As each item is selected, it is removed from the population. So we don't want to repeat the second sample element as the first or previous sample element. So we should remove from the population. Means what we do is select two numbers from between 1 and 10 without replacement. If we get first time 9, then we should remove 9. Then second one should be between 1 to 10 without 9. Sampling with replacement, if we allow replacement, then it can be again the first one also sometimes. So always your population is constant from which you are randomly picking for replacement. Without replacement, whatever is picked up from the population, that element is removed for the second random selection. So objects are not removed from the population as they are selected for the sample. In sampling with replacement, the same object can be picked up more than once. So that is natural because you are allowing same element can be picked. So sometimes you may see both same element twice or more than once in that sample with replacement. So can any idea where do we use in real life this sampling with replacement, sampling without replacement?
whenever we conduct any surveys, we'll not
Okay.
pick all the people. We'll select some random people, and those results we say that they are applicable to the entire population. That is random sampling without replacement.
So whenever you want to take survey, then no meaning of taking the same response from the same person twice, right? That is good. Good example. So where do we require this sample with replacement?
Examinations, like for example, if a student is allowed for one exam, for the next exam also you should compulsory write, means there should be a with replacement for it.
Not compulsory, right? Here we are talking about the random thing, right?
Okay.
So when you insist compulsory, then it won't become random. When you are assigning tasks, small tasks, one person can do many tasks in a day. Then I don't want to differentiate that. It's even if I am okay with assigning 3-4 tasks for one person, then I will allow replacement there. Then some people may get one task, some people may get 2 tasks, because I am allowing replacement, right? For first task, I will assign for one person, then second task again. Second task is again, it's anybody can do, including the person who got the first task. Then we can use the sampling replacement.
Yes.
Then another type of sampling is stratified sampling. So this stratified sampling is important to get the representation. So what we do is in stratified, when we are selecting a group of people from your class, if I want it should represent, then I should first divide your class into male students, female students. Then I need to take sample from male as well as female. So that is stratified, means you are putting into boxes the population, then you are again randomly selecting. Split the data into several partitions. Then draw random samples from each partition. In simple thing, if I want to select 10 numbers from 1 to 100, randomly pick 10 numbers. Then what is stratified sampling here? Which is the best stratified sampling?
Divide into 10 range and pick
10
randomly.
parts. Yes. Then I'll get the small number to higher number equally well, right? I'll get one number between 1 to 10, then 10 to 20, like that. So that is called stratified sampling. It represents the entire data. So if I get mean, then that will be close to mean of the 100 numbers. Otherwise, it won't. So stratified sampling is used to represent the sample, to represent the population. Then what sample size is necessary to get at least one object from each of 10 equal sized groups? So in statistically, even if you don't stratify, still you can get, but there is probability will involve. Then it's saying what sample size is necessary to get at least one object from each of 10 equal sized groups. Just now we discussed 100 divided into 10 parts, then get one sample from each. If you don't divide, and if you want to, from each bin or bin of 10 numbers, one sample should be there. Then your sample size, if you want 100% sure, then at least 60 numbers to be selected randomly. I'm not going into details of proving these things statistically, but try to understand. If you don't stratify, means put 10 groups and select one, randomly select some number of elements, what is the guarantee? 100% guarantee, almost close to 100% guarantee that one sample belongs to at least each bin of 10 will have one random sample selected. For that, at least you need to select 6 to get that almost 100% surety, 60. Then okay, 95%, then 50 numbers should be selected randomly. Then if you want 85% of confidence that it's each bin should have one randomly selected element, then you should take 40. So if you take simply 10 elements, what is the probability that it's each bin have one element in random sample? See this graph and tell me.
Almost near to 0.
0 means you may not get.
There
Then
is
if
only
you
one
take
chance we'll get.
One chance,
Yeah.
0.1.
0.1 is also doubt, right? At 10, it is still at 0.
One
Point-
in,
point
one in
zero
100,
zero one.
0.01.
0.01.
It's very small, right? So almost there is no confidence for us actually. Most of the times we won't see that. Then if you take 20 sample size, then what is probability?
0.2.
Point.
So out of 10 times, 2 times you can find these samples spread over into all 10 bins. So the sample size also matter. So now to get your sample representative, whether to increase the sample size or whether to take the stratified sample. That depends on your domain, where you are applying, how much of resources you have. If you can handle 16 sample size, then you don't need to worry about, again, it's stratifying the data set. Stratifying has its own complexities. 0 to 100 is very easy for us to divide it, say 10 bins. If you have no ordered numbers or no ordered like something like which cannot be comparable, those things, then how do you divide? Then again, random divide will come. Then that is almost equivalent to random selection. So sometimes it may not be that easy to stratify the things. Then you need to go by this, if you can handle that big samples.
So this is the reason why we do the split as 60-40 machine learning data set. Why we select at least 60% of the training set so that we get the representative data. So this is the reason, right?
Yes, that minimum this 60 is giving 100%, almost 100% clarity, right, for us.
Represent.
Yeah. Not in imbalanced data sets again.
Yes.
In imbalanced data sets, we need to go with the stratified sample only.
Yes.
Because it's in imbalance, what happens? If you make 10 bins, one bin still have some less probability, right? It is not almost 100.
Yes.
That you have 0.001, whatever that it's or 0.1%. Then that 10% is your bin, right? In that 10, that 1% is minute again. You have guarantee that in 10% you get the sample, but not in that 1% again.
Right.
If you make 100 divisions, then this number will again increase, right? Then you need to get 100 divisions. Each division should have one representation. If it is only 1%. You understand what I'm saying?
Yes, sir.
So imbalanced data sets should be careful. As you said, you brought a very good point. Thank you. That it's in general, if data set is not imbalanced, you have equal number of positives, negatives, whatever that, then this 60% will give some guarantee for us that it represents the whole sample, whole population. Good, thank you. So that is regarding sampling. Then coming to the discretization. Yesterday we discussed about attribute types. Their discrete attributes and continuous attributes we discussed. So what is the meaning of discrete attribute?
Countable value, finite.
Between any two consecutive values, there will be finite values.
That is
We can
wrong.
predict the next values of between and
So if we can know that what is the next value, then it is called discrete. If you can put them in order, then those values are, it may be infinite, we don't have any problem. But we should know that what is the next element. If it is integers, I know that what is the next element after 3, 4. Whereas it is real numbers, I don't know that what is next. Of course, there is no next. That is, infinite numbers are there. Whatever people say, then I can still find a middle number of that. So they are called continuous. So when we are dealing with decision trees, we may need to convert our continuous attributes to discrete attributes. There we need discretization. Means how do you make them into groups that continuous instead of representing with real numbers? How do you make as a groups then? We'll discuss that here. Discretization is the process of converting a continuous attribute into an ordinal attribute. You can still contribute. What is ordinal attribute meaning?
Comparable, if you can say greater than or less
You
than.
can still compare.
Equal.
This group is less than that. Yeah. A potentially infinite number of values are mapped into a small number of categories. So any value between 0 to 100, real numbers, what I do is I make 10 bins, like 0 to 10 as first group, 11 to 20 second group, or anything more than 10. Because I'm stopping at 10 real numbers, I don't know, it's a way to start. So I say that there is some mathematically, there is symbol. If you take this square bracket, then that includes number. See, this is so if you have this 10 comma, if you have something like 100, what does it mean? Any number greater than 10 is included, but not 10.
Yes, sir.
If you use this bracket, then 10 is not included. What about 100?
100 is included.
100 is included. Whenever you close with the square bracket or start with the this square bracket, that number is included. That we should remember, right? So then when we represent 10 bins, then we will start with 0 square bracket, 10 open bracket, or 10 close bracket. If you use the 10 close bracket, the next one is open bracket with 10, then close with 20, like that.
20.
Okay. Discretization used in both unsupervised and supervised settings. In both algorithms, we may need this. So if you come to the unsupervised discretization, in two ways we can do this. Supervised method we can use, unsupervised method we can use. In unsupervised, we don't worry about how the class is changing because there will be no class there. You are just dividing your numbers into groups. If it is supervised, then you should also take care that your classes also should fall into the same percentage or something when you divide them. Then that is called supervised. We'll discuss more now. Data consists of 4 groups of points and 2 outliers here. Data is one-dimensional, but a random Y component is added to reduce overlap. Okay, here it is shown that it's a I will remove this. Okay, I'm unable to remove that. It's okay.
Sir, if you stop and start sharing.
Okay. So in unsupervised discretization, here some example is given. All this is one-dimensional, but he's saying that it's a lots of points overlap one and another. Some random Y's means all these points are at 5 only. All these points are at 10 only. You should think like that. Data consists of 4 groups of points and 2 outliers. You know what is meaning of outlier, right? What is meaning of outlier?
Which is varying more.
Yeah. Which is very far from the normal behavior of the data. Normal behavior is the data points between 4 and 16, right? But this is extreme value, it is taking 0, other one is taking 20, means they are very far from the normal behavior of the data. Those points are called outliers. Here in this, we have 2 outliers. Then in unsupervised discretization, what will happen? Let's say we want, suppose 3 groups. Then we randomly draw these 3 lines here. Then whatever left side is 1, then between 5 and 10 is the other group, or between 10 and 15 is one more group, and 15, 20 is one more group. So equal interval width, we only take the smallest value for that attribute and the largest value. We just make that entire interval into 4 groups. So equal interval width approach used to obtain 4 values. This is called equal interval width discretization. Then equal frequency approach used to obtain 4 values. Instead of width, what we take is, there are 100 points. Wherever the first 25 points ends, there we will put 1. Then 25 to 50 points, means we will sort them, and we are not equally dividing that our interval. We are dividing equally points now. So we will count up to 25, whatever number, 25th point, maybe at 30th in the position, then 30 is one partition for us, 0 to 30. Then if you find 25 numbers between 30 and 40, next 25, then second discrete component will be 30 and 40 only. It is not equal, we are going by the frequency. So all the elements for that attribute are sorted, if they can be sorted numbers. Then put equal frequency bins, not the equal width bins. Is it clear the difference between equal width and equal frequency?
Yes, okay.
Then k-means approach to obtain 4 values. You know anyway k-means algorithm. Then take, if you want 4 groups, then take k equal to 4. And by distance wise, whichever is falling into those clusters, make them as 4 groups. Is it clear that k-means? Because we have already done k-means, right?
Yes, yes.
So you can cluster them into 4 groups. That is based on distance. Discretization in supervised settings. We haven't considered anything there class variable, right, earlier. Now in supervised settings, how do we do discretization? Many classification algorithms work best if both the independent and dependent variables have only a few values. We give an illustration of the usefulness of discretization using the iris dataset. So the first point, what it makes clear, see, in many classification algorithms, work best if both the independent and dependent variables have only few values. So you cannot put in one bin all the positive values, in another bin only negative values. If such thing happens, then it is not a good discretization. So they may not work that good. So both should have few values. So here, if you take one example, iris plant dataset can be obtained this where you can get this dataset. So from the statistician Douglas Fisher, I started this, giving this example. Then 3 flower types, setosa, versicolor, virginica. So if petal width and length are given, then we should be able to predict whether it is setosa, versicolor, virginica. So the features will become petal width, length. So for 4 non-class attributes, sepal width and length, and another one is the sepal, and the one more thing is the petal width and length. So if you get 4 attributes, you should be able to classify them into those 3. Then how can we tell what the best discretization is? Whether each width is taken, sepal width into 4 bins, something here 8 bins. Each attribute you can put into 8 equal width or equal frequency. That is the unsupervised. So unsupervised discretization find breaks in the data values. Example, petal length. If you take petal length, then you can divide them into like this. So then it is not equal frequency. So in one bin, there are many. In 2 to 4 bin, there are very few. Like that, it is not dependent on the frequency. Supervised discretization use class labels to find breaks. So you need to get class. So I am not interested, whether it has more, equal width, equal frequency. I see that there are 100 elements are there. Then I am interested in positive thing. Then if I get 20 positive, then I'll make 25 positive. Then next 25 positive, next 25 positive, like that. 100 positive things are there. Then I'll divide the data into 4 bins based on class. Use class labels to find breaks. Then here, petal width low or petal length low implies setosa. So if both are less, then the classification is clear here. Then your bins should be like this, because if you are interested in setosa, then setosa should also be discretized, right? Based on that. Petal width medium or petal length medium implies versicolor. Petal width high or petal length high implies virginca. So even if you go with unsupervised, it gives clear distinction, because you get the same boxes, right? Petal width low and petal length if you make equal width. The first one is the low. For both X value and Y values, it is low, right? First box. As you move, then here for both it is middle. As you move right side, for both it is high. Even equal width will work here fine, because the classification is such that they are very smoothly divided. Like if both are small, if both are medium, if both are high, then our equal width also will divide like that only. Here it works fine, but sometimes it may not work. Then we may need to take the class as a variable when we are doing discretization. Then another thing is the attribute transformation in pre-processing, data pre-processing. So why do we need to change attributes to 1? Because we have discussed in logistic regression or linear regression, we are assuming the data is linearly dependent, right? Dependent variable is linearly dependent on independent variables. If the dependent variable is not linearly, then we will try to transform the independent variable, see whether after transforming that independent variable, whether dependent variable is linearly dependent or not. Then our algorithms works fine there, because our assumption is the data is linearly dependent. So an attribute transformation is a function that maps the entire set of values of a given attribute to a new set of replacement values, such that each old value can be identified with one of the new values. So simple functions, instead of x, that we will create another column x power k, then we'll compute for each value x power k. In that column, we will fill up with those values. Or logarithmic transformation, e power x, mod x. So most of the times x may not be that the dependent variable or response variable may not be linearly dependent on independent variables. But if you take log, then it may become, because logarithmic will become linear. So you might have seen it's in algorithms when we discussed about the algorithmic complex time. Then when you take the log values are linear there, the complex time. So that is called logarithmic linear. So when you take the log, then it becomes linear. So normalization, you can take some examples are given. You can take polynomial transformation or logarithmic transformation or exponential transformation or mod value. So if you are not interested whether it is negative or positive, you can simply take the quantity. What is quantity important? Then you transform each value to mod x. Some of the things you can get back, some of the things you cannot get back. If you lose the data x power k, there will be k roots, right? For x power k, you may not get exactly from which value you got this x power k. You understand what I'm saying?
Yes.
Whereas e power x, you may get the exact value back. Sometimes you can get back your value. That's why you may need to keep the data also. When you transform and when you don't use the previous value, still keep the data. If you want to go back, some of the transformations, it is not easy for you to go back. Normalization refers to various techniques to adjust to differences among attributes in terms of frequency of occurrence, mean, variance, range. Take out unwanted common signals, example, seasonality. Anyway, normalization we discussed to get the same scale and for all of the variables, that is important. So we may need to do normalization of them. And one advantage they are saying here, take out unwanted common signal, take out unwanted by normalization, what will happen? Take out unwanted common signal. So seasonality can be found something. So we'll see examples whenever it comes in the coming slides. In statistics, standardization refers to subtracting off the means and dividing by the standard deviation. This is called standard scalars. Then sample time series of plant growth. Net primary production is a measure of plant growth used by ecosystem scientists. Then say Minneapolis, Atlanta, Sao Paulo, Brazil. Then correlations between time series. So 82, 83, 84, you have the values. So if you take these values, find the correlations, then for Minneapolis versus Minneapolis, it is almost 1 because same. Then Atlanta is 0.7, then Sao Paulo, it is minus 0.75. It's statistical parameter, this correlation, there is formula. If you give these values, Minneapolis values and Atlanta values, you'll get correlation between them. It is symmetric matrix. Correlation between A to B and B to A is same. So seasonality accounts for much correlation. So normalized using monthly jet score. So what they did for each monthly, on month basis, they see in Minneapolis, they might have computed plant growth in some scaling. Atlanta is some scaling. But when you normalize for each variable, this normalize each variable values. Minneapolis is one variable or whatever that Minneapolis values. Based on Minneapolis values, you are normalizing. Similarly for Atlanta, for similarly Sao Paulo, Brazil. Then when you normalize, what is the correlations you can see here. So what is the difference? Correlations are changing now. Earlier correlation between Minneapolis and Atlanta is 0.7591. It is only 0.0492. So there was highly correlation earlier between Minneapolis and Atlanta because one is the high, right? It is almost 3/4 of or 1/4 close to only 1/4 distance or 3/4 close to 1. Whereas when you did normalization, then you found there is absolutely no correlation, 0.04, it is close to 0. So that is what you are able to see here. The normalization will actually change the correlations. So take out unwanted common signal and seasonality. So here they are saying that they might have removed seasonality by normalization. That's why you see that there are not much correlations you are able to find. This is regarding normalization and its advantages. Then coming to the dimensionality. This word is very important, curse of dimensionality. It is always trouble for us if you have more dimensions. The first problem is how to visualize the data, how to present the data. You cannot have more than 2 to 3 dimensions to present the data. That is one problem when you have more dimensions. And your algorithms also will become more intensive, time-taking algorithms. Third, if you have more, then more noise also will come. They may be unwanted features. They may not be contributing anything to the response variable, but because of we are putting them, then we are trying to adjust our mathematical formula, considering that actually disturbs the algorithm. That is another problem. So unwanted features. So this dimensionality in data science, it is called a curse. If it is increasing, then you cannot handle that in a smooth way. When dimensionality increases, data becomes increasingly sparse in the space that it occupies. Then data also, you can see that unconnected dots, something like that. So data becomes sparse. That is also one problem. Definitions of density and distance between points, which are critical for clustering and outlier detection, becomes less meaningful. Even to find clusters, to find outliers, it becomes difficult because the data becomes sparse. Nothing will look like they are close. So that is the problem with the high dimensions. So now here some example is given. Randomly generate 500 points. Compute difference between max and min distance between any pair of points. Then if you take 500 points, then it becomes very difficult. If you take only 10-15 points, it becomes simple to compute. It's a difference between max and min. So how to handle this dimensionality problem? So we can reduce the dimensions. The purpose for the dimensional reduction is avoid curse of dimensionality, reduce amount of time and memory required by data mining algorithms, allow data to be more easily visualized, may help to eliminate irrelevant features or reduce noise. We discussed all these points in the previous slide. Techniques. What techniques we'll use for this dimensional reduction? One is the principal component analysis, which we have studied in machine learning. Single value decomposition, which we will study in data mining, SVD it is called. Both are mathematical based methods. Other supervised and nonlinear techniques. So supervised techniques is you will find out whether that is contributing or not. When we discussed about logistic regression, linear regression, we have seen F value, whether F value is same, whether you remove this feature or not. If you remove that feature, still F value is same, then that is not that important to be in the part of the algorithm. Like that, they are supervised. And some nonlinear techniques are also there. You may combine different features to one feature. Like in PCA, you are combining or creating new features. So there are some other nonlinear techniques. In documents time, you can see that nonlinear matrix, non-negative matrix factorization, NMF, topic modeling that will come there. So different techniques are there for the dimensional reduction. This PCA, then you are transforming your original dimensions to new dimensions so that they can be ordered new dimensions with high variability to low variability of the data. On which axis you find high variability in the values, in which axis you have less variability. So in which axis you have less variability for the data, those axes or those dimensions will be removed. That is the PCA. So in this dimensional reduction based on PCA, so you can see that what will happen, if you remove the dimensions, still you can see some human is there in this. This is lossy compression again, you may not go back, but still some of the properties you'll get. Then dimensionality reduction, this is for 8 features if you take. If you take only 4 components, you'll get like this in PCA. 8 components you'll take like this. This is 8. This is 16 components. You're still able to look at great. 32. Then the difference between 16 and 32 is how much? When you compare with 8 and 16. When you go with 4, there is no absolutely not identifiable, right? The images.
Yes.
Yes, sir.
When you take 8 components, you can identify it as a human, right?
Right.
When it comes to 16, you almost got whatever you need to find in that, right? It may not have clarity, but you got all the features of that picture. You can say that it is a female looking at whatever that with cap. All those things you can clearly identify. Then from 16 to 32, how much of difference is there? It's only clarity, not the properties you find extra, which you cannot find with 16. Am I right?
Yes.
So 32 to 16, you can reduce here. Means you can take only 16 principal components instead of the 32. If you want this much of clarity, is good enough. It depends on what problem you are doing, right? If you want to identify just what is she wearing, then you don't need to have 32 things. So that is good enough. But if you want to see the skin color, skin smoothness, whatever that it's, then you may need 32 or even 24, whatever that it's, the middle. And other parts, what color of hair, all those things. So it depends on which domain, which problem you are working, how many principal components you need to take. So now you see the difference between 32 and 256. How much difference is there? This is 32. This is 256.
Clarity.
Clarity, right? You can have, if you want to find out each and many finer properties, you may need this. It depends on it, say what problem you are doing. Then how do we reduce these dimensions? One is the feature subset selection. Another way to reduce dimensionality of data is redundant features, duplicate much or all of the information contained in one or more other attributes. So if attributes itself dependent on other attributes, in databases, you know that it's, if one attribute dependent on, it's a normalization, you will see that it's, those attributes shouldn't depend on other. So here also, if your features are dependent on other features, though you are calling independent, if they are not independent, you can remove them. Example, purchase price of a product and the amount of sales tax paid. Because sales tax paid is computed from the purchase price only. So that's why you don't need two columns. Even though you have two columns in the original data, you can remove one sales tax thing because sales tax can be computed from the purchase price. Irrelevant features contain no information that is useful for the data mining task at hand. So anyway, some features, if you feel they are not contributing anything, they are irrelevant, remove them. Example, student's ID is often irrelevant to the task of predicting students' GPA. It may be the previous grades, how he is getting in different subjects is important, but not his rule number. So the rule number column you can ignore. That is irrelevant feature to predict GPA. Many techniques developed especially for classification. Feature creation, you can also create new features, create new attributes that can capture the important information in a data set much more efficiently than the original attributes. Three general methodologies: feature extraction, example, extracting edges from images. So this, it's when you do the deep learning, it's a different layers. You are actually creating different features. Each layer you can think that you are creating a new features. So when you do the convolutional neural nets, so in the first layer it will get edges, second layer it will get something little bit above than the edges, what is there like that. So extracting edges from images, feature construction, dividing mass by volume to get density. So sometimes you may get mass and volume two different values, but that may not be accurately helping us. If you know the density, then you may get more value out of that. Something like population may not give you, how the facilities are good enough. So if you know the density of the population in an area and the facilities, then that will be good for you to predict how comfortable the people are. So then you need to find out density, not just the area and the population. If they go individually, they may not give you any predictive power. But if you compute this density, it may give you predictive power for some objective function. Mapping data to a new space. This is again a transformation of the variables. Whoever has studied this Fourier analysis, wavelet analysis, we will transform from frequency to time to frequency. Then we compute there, we'll come back. So like that, here also you can convert or transform your variables from one representation to other representation. So mapping data to a new space, Fourier and wavelet transform, 2 sine waves plus noise. If you map them to frequency, this is time-wise, then you are getting a very neat graph here. Then it looks good to analyze what's happening here. It also removes the noise when you transform. It's more intensive mathematics, actually, whenever you are interested. Some of the times in data science, we may require, particularly this electronics-based things or communication-based things, speech recognition, those places, this frequency and time is important. So convert from time to frequency, frequency to time. So this completes our discussion on data pre-processing. Any doubts regarding this data pre-processing?